So I recorded this already once. I thought I had the recorder on and I didn't, so this is my second time through. This is going to be a little introduction to epsilon proofs, which is the bread and butter of Real Analysis Junior, which is what we call baby analysis, which is the analysis you're going to take here as a math major. Hopefully, you should take it. And then if you're in a graduate program, they'll ask you, do you feel comfortable with baby analysis? And if you say no, they'll put you in the baby analysis class, and you'll be one step behind. So our goal is to get you to be comfortable with analysis when you take it here, so that when you do enter a program, you can enter right into the big people analysis, Real Analysis Senior, which they do epsilon proofs, but not to the degree that you do it in Real Analysis Junior. So I'm going to bring you back to the definition of soup. Recall that our definition of soup that we worked with in class is that it's number one in upper bound of the set. So that means that for every x belonging to the set, you have that x is smaller than or equal to s. And number two, if u is any other upper bound of a, then that s has to be smaller than or equal to u. So it's like a West Point soup. It's the best of the best upper bounds. So I'm going to show first how to use this definition in a proof. And we're going to prove something that seems very obvious. As Ariana would say, every 6-year-old knows this. Very smart 6-year-old if they know about the real numbers, but let's say every 6-year-old knows this. Anytime you think like that, it's going to be probably hard to prove because you really have to go back to basics. But here we have an interval in the real line, and we're going to prove that B is the soup of I. And so you guys did this already on a, not proving it, but you actually plucked out the soups on an in-class assignment where A and B were real numbers, not actually plugged in numbers. So the first step is to write that as an if-then statement. So if I is equal to that interval, then B is equal to the soup of I. Extract the no right from the proof sheets. I is that interval. I'm going to go to the 2 steps ahead and just expand that no. That I'm going to write as set notation. It's the set of x's, and I really should have put x belonging to R here, such that x is between A and B. Why would I do this? Why would I write it like this? Well, it gives me something to work with. Now I have an inequality where before I just had this open interval, which I can visualize, I can understand, I can pull out the soup for you, but I have nothing to work with. So now I have something to work with. It's an inequality. So I'm going to take my no and then rewrite that thing as an inequality. And this should really be if and only if. X is an I if and only if x is between A and B. My show is B is the soup of I. That means I need to show 2 things. First, that B is an upper bound. And second, if there's another upper bound, then B is smaller than or equal to U. These are daunting things, actually, when you think about it. Like I even sit there for a second and go, what? There's almost nothing I have to work with. But the first thing is to notice that B is bigger than or equal to x for all x and I, because I can see that right from my interval definition of x, of I, right? I have that all x's must be lower than A, bigger than A, or smaller than B. So it's certainly smaller than or equal to B. So by definition of I itself, I have, the inequality definition, I have that B is an upper bound. So number 1's resolved. You can't see me, but my thumb is up. Done. That makes me worried because number 2 is usually more difficult. Okay? Well, I'm supposed to show if I do have another upper bound, so let's let U be another upper bound, then I have to show that U is bigger than or equal to B. That's kind of hard to do. You can think about this for about 5 seconds and realize I have nothing to work with again. So if you think about it just a little bit longer, you would start to think, well, there could not be such another upper bound, because if there was, it would end up dipping into my set. And so that's what I'm going to do. As soon as I say something like that, it makes me think about proof by contradiction. If I had another upper bound and B was not smaller than or equal to that upper bound, then the opposite must be true, that U must be strictly smaller than B. So let's assume that there exists some monster like that. Well, either U is going to be somewhere over here. If it's over here, it's smaller than any element in the interval, so I'm going to get a contradiction immediately. But what if I dip down just below b, like this? I plan to show that if something happened like this, it's going to disqualify u as being in an upper bound, because u is supposed to be an upper bound. So what I really have to do is I have to show that there's an animal in here between u and b that's in the set that's going to be bigger than that u, because that would disqualify it from being an upper bound. So first case, u is somewhere below a. Then we're done, because u is smaller than x for all x in I, so it cannot possibly be an upper bound. So the second case is that u somehow ended up between a and b. We're also done then in that case, because u must belong to I, first of all. So u's in there. And I'm going to find you an element right here that's strictly between u and b. U is smaller than b. There's an n large enough, so I can get u plus 1 over n is strictly smaller than b. Right there. Some people may make you prove this. So Dr. Williams may make you prove that. So then that adds another layer of proving things that are obvious to this. Since u plus 1 over n is smaller than b and bigger than a, I know that it's an element of I by my inequality definition of I. So u then is smaller than y, but y belongs to I. Well, then that disqualifies u from being upper bound, because u was supposed to be bigger than y. And I wrote it out here in words. That creates a contradiction, because u was supposed to be bigger or equal x for all x in I. And I found an x, called my x y, where u is smaller than x belonging to I. Thus, my assumption that u is smaller than b is false, and therefore the opposite is true, so b must be smaller than or equal to u.